All right, everyone, we're doing the practice exam 2 for OChem 2. So predict the product. One strategy we always want to use with carbonyls, I'll just do it for the first one. We want to draw the Zwitter ion. That shows the reactivity of the carbonyl. So we see our positive and our negative charges. Our Grignard reagent here with the lone pair on carbon can go ahead and attack that positive charge from the carbonyl. That'll get us to about this state right here, where we have added 2 carbons. And then we just acid quench it to give the following product. So we'll end up getting this alcohol that's tertiary. How do we make this is called a cyanohydrin. You don't need to know that name. The way we make these is through NaCN and HCN, which is added to a carbonyl. So the carbonyl will go ahead and get attacked by CN- in a similar mechanism to give something like this. And then HCN will just protonate it to get the final product there. This is a Wittig reaction. These pieces are kind of just going to connect together like Legos. So another way that we can draw this right here is by doing that. That's the equivalent. So we can just go ahead and connect these together like Legos to give this product. We end up making the trans product, which is the more stable product, by the way, because this is a more stabilized ylid due to, it's not how you spell that, ylid, due to the fact that we can go ahead and do resonance here like this. So we make that final product just by connecting the Legos together, basically. This next one, we're just adding a protecting group. This is a acetal formation, which is a really involved mechanism. I'm not going to draw it yet, but we'll go ahead and just add this onto the carbonyl. So whatever this was, we have this same group, ethylene glycol, on top of there. So we end up getting that product. Here, so we can go ahead and draw some of the mechanism for this. I have a lot of room for that. So we add it, right? I think it's obvious here that once we add the amine, we want to deprotonate it to get rid of that positive charge, which isn't super good. And then we do now we have positively charged acidic amine that can go ahead and protonate our OH. So now we have an OH in the molecule. Usually in amine mechanisms without acid, we go ahead and kick out the hydroxide by itself. And then here, right, because we don't want to end this product with a positive charge in the amine, we can go ahead and deprotonate one of the alpha protons to make this amine neutral with a lone pair instead. So this is called an enamine. And we go ahead and make that because we don't want to have that positive charge. Positive charges are not good, at least in our final product. All right, so starting here, the first thing I want to add is I want to add magnesium to make a strong nucleophile here. So magnesium will get added to make MgBr, and then to add our carboxylic acid, we just want to add CO2. So CO2 and then H3O+. I'll go through the mechanism here. So our Grignard reagent, that lone pair, goes ahead and adds the CO2 into the molecule. And then we can simply protonate that in an acid-base step to give the carboxylic acid. Here, chromic acid, we don't need to know the mechanism for this. It's simply going to oxidize whatever nearby carbons to a carboxylic acid. So here, this has enough room to still have, so this carbon will not exceed an octet, by adding a carboxylic acid there. So we can add a carboxylic acid onto that, into this little methyl group right here. If we tried adding a carboxylic acid to here, this would be, this is terrible, so don't draw this, but we would end up getting something like this, where we would have like 6, 7 bonds on this carbon. That's not going to happen. So this would require C to C bonds breaking. If we formed a carboxylic acid there, the general rule is you don't want to break C to C bonds here. You just want to make a carboxylic acid at primary. At primary carbons near benzene rings. So near specifically the benzene ring. That's because this mechanism goes through a radical, and you need to have resonance stabilizing that radical. If you don't have that benzene, the reaction just doesn't work. This is a Fischer esterification, the next one. So Fischer esterification. The secret to these is you just want to get rid of the O. Just, matter of fact, just get rid of the OH and then just replace it with your alcohol. So just your alcohol, whatever was there, you just want to replace it there. The reason I removed the proton is because if we still had it, that would be positive, and we don't want that. So we want to have O by itself, neutral. And we'll talk about the mechanism for that soon. So Socyl 2, when you add that to, thionyl chloride, when you add that to carboxylic acid, you get an acid chloride. This next one, you probably need 2 equivalents. I didn't really specify. The first thing that this is going to do mechanistically, because this is a little bit challenging, I will go through the mechanism. We have a pretty acidic proton that the Grignard is just going to deprotonate. So we actually covered this in class Wednesday, which is the day I'm recording this. We make this carboxylate, which isn't super electrophilic, but Grignard is like so strong as a nucleophile, it doesn't even care that the carboxylate's really weak. And we end up getting something like this. We have acid, which is indicated in the problem there. That will go ahead and make this hydrate. And then when you add more acid through a different mechanism, it will go ahead and make the carbonyl. So essentially what we're doing is we're replacing that OH here with a carbon-containing group of the Grignard reagent. So that's our final answer there. All right, we're going to name these molecules according to the IUPAC nomenclature system. So for carboxylic acids, you always want to start with the carboxylic acid on the number 1 position. That'll always be the case. You can always do that. Here, right, because we have a ketone, this is actually going to be an oxo substituent. So normally we'll name those we'll name molecules based on the highest priority group. A lot of the times those are ketones, but here carboxylic acids are the highest priority group we've learned so far, so that will take precedence. So here we have 5-oxo hex 2-ene oic acid. And I don't have to indicate the position of the carboxylic acid since it's assumed that it's always going to be at the 1 position. And then I can't forget that this is an E alkene. The next one, so we're naming this IUPAC molecule. It is 5 carbons. This is a hydroxy group, so it's 2-hydroxy pent. And then this is a aldehyde, so we will name it like the following, pentanal. We do not need to indicate actually the positioning of the aldehyde because it's an aldehyde, so it's always at end. It's always at the end. We do need to indicate RS. So here, directly attached to this carbon is an oxygen. This has an oxygen too. That will end up being an R stereocenter. So it'll be R2-hydroxypentanal, like that. All right, so just a mechanism for the following reaction. This is a Wittig reaction. The The way that this reaction works is that we're going to have to draw a key resonance structure here that explains the reactivity. It gives us a positively charged phosphorus and a negatively charged carbanion. The carbanion can go ahead and attack the carbonyl like that. Let's see here. That'll go ahead and make this molecule. So important to number your carbons here so you don't screw it up. So we're attacking at the 2 position. And then we'll have 1, 3, and 4. Like that. And then we'll also have a... Actually, this isn't super well drawn, to be honest. So I'm going to redo it. Something like... So we're just drawing the original molecule here. The positively charged phosphorus, and then we just have a methyl and an ethyl group coming off. So something like that. It may seem obvious to you that negatives attack positives, so that is going to be what happens in the next step. Like this is getting a little bit complicated now, but essentially what's going to happen is oxygen is going to take its lone pairs. It really likes to bond to phosphorus. To make phosphorus not exceed an octet here, we are going to go ahead and... So it actually will exceed an octet, but to make sure it's neutral in the final product, we'll end up donating those electrons in this bond back to the alkene. And that will form this alkene. Because this is unstabilized, there's no resonance in the ylid form. That makes the cis or unstable product, which we'll talk about right now, actually. It made the less stable cis-alkene product. Why? Drawing a picture in a few words is a sufficient answer. So here, right, the answer is... When we draw the resonance structure, here's the picture I wanted you to draw. When we draw that resonance structure, we end up with non-stabilized ylid. So I'm going to say non-stabilized reagents give non-stable products. And then we'll say the reaction is irreversible because of that. Because the reactants are really unstable, the reaction's irreversible. This by itself won't be able to act as a leaving group, and therefore, once the phosphorus is inside the molecule, it just will not be able to leave. So once you get past this committed step and make the cis-alkene, you're not going to be able to undo it. All right, another mechanism we actually know, the Fischer esterification. I'm going to go ahead and draw the catalyst. So here we have a isopropyl alcohol that's protonated. We can go ahead and protonate the carbonyl with that. You should be asking yourself, what is the purpose of protonating the carbonyl? That makes it a better electrophile. So now we can have one of our alcohol nucleophiles come in and attack. That will then make this hydrate, which we've actually seen before in one of those predict the product questions. We have a OH with a positive charge. We want to deprotonate that. Whenever you see that, you want to deprotonate it generally, unless it can leave. Here it can leave, but to get to the final product, we do want to integrate that, so we don't want it to leave, really. Now we have too many OHs. So to get from 2 OHs to 1 O, we need to lose water. And the way that we're going to do that is by taking some of our acid and protonating one of the OHs. Now that can leave in a resonance stabilized intermediate to form this carbocation. And then we can go ahead and draw a resonance structure where some of these electrons go down and form a pi bond. And then we ask ourselves, what's separating this from this, it's simply just a deprotonation step. So we can go ahead and do that. And that will go ahead and make our product there. So KEQ is around 1. That's because delta S is equal to 0. Delta H is equal to 0. You didn't really need to know that. This is a side thought. We're forming this. If you do the bonds broken bonds formed analysis, you'll see the bonds broken are identical to the bonds formed. So KEQ is equal to 1. Delta S is 0. So there's nothing really driving this. We drive this using Le Chatelier's principle. So we add more reactants or remove products to drive formation to the right. So to compensate for the fact that we're not really forming much at equilibrium, we want to keep the reaction out of equilibrium by just adding a ton of reactants that can go ahead and react. Or we can remove products. So we can, like, say, you guys have done this in lab. We can use, like, calcium chloride or sodium chloride or something like that to get rid of water. We can do that and then make more of the ester product. All right, good old synthesis. So remember, we want to work backwards, right? You always need to work backwards when you're doing synthesis, especially at this stage in the game. We have like 50 reactions we know. You guys don't think about that. We have 50 reactions. You'll never be able to guess at this stage in the game. You'll never be able to work forward and guess what the reactions are actually going to be. You need to work backwards. With that being said, right? So what do we know can make C to N double bonds? So we've seen this chapter, and most of the reactions in synthesis are going to be in this chapter. But when you add an amine with 2 hydrogens and then 1 carbon-containing group, you can actually go ahead and replace a carbonyl with that. So carbonyl will go ahead and get replaced by the N to make a C to N double bond. The question is now, how do we make this? And I see there's many, many different ways to do this. So the way I'm going to do it is I'm just going to say we had an alcohol and we use chromic acid to go ahead and oxidize it. How do we make that alcohol? We've actually seen this. We can use Grignard reagents. So a Grignard reagent, we'll go ahead and add to that, and then with an acid quench, we can go ahead and make that alcohol. Now the question is, how do we make this aldehyde? Right? Do we remember how to make an aldehyde? And it's actually a little bit similar, right? So we can use this aldehyde. I'm going to use a reaction from last semester. There's other ways to do this I'll talk about as well. We can use BH3H2O2 to use that, to make that aldehyde. And then we can just take our good old first carbon forming reaction, carbon to carbon bond forming reaction, which use acetylide and NaNH2 to do that. That's personally how I would approach this synthesis, just because we have used that a lot. Is there any other ways to do this? Of course there is, right? So to get to this stage, actually a pretty good idea here would just be to use 2 Grignard reagents with a acid chloride like this. We haven't seen this reaction explicitly yet, but we have seen a process where nucleophiles can displace leaving groups through a tetrahedral intermediate. So that would actually lead to this as well, but that's up to you. This is technically a chapter 19 reaction, which is why I really don't want to use that in the synthesis, but you could do that if you wanted to. But there are multiple ways. As long as you're using valid reactions, you're getting full credit on the synthesis question. But this is personally the way I do it. It uses a lot of the synthesis reactions we've already seen. All right, so starting from 3 carbons or fewer, we need to make this. The way I'm going to do this is I'm going to make a carboxylic acid first, and then do Socyl 2 to make that into an acid chloride. Oops, I meant thionyl chloride, not Sockle 2. How do we make a carboxylic acid? There are several ways to do this. One way is through a carboxylic... So, one way is to make carboxylic acids through CO2 and adding acid. How did we make a Grignard reagent? We took something with Br and then added Mg. Now, how do we add Br to a... How do we make a primary bromide? Last semester, we used HBr and H2O2. Of course, there's different ways to do this, but that's one way to do it. How do we make an alkene? We do an alkyne, so we do an alkyne and then Lindlar. Or you can also use sodium metal and NH3 liquid. You could also do that. At this point, it's just synthetic reactions we actually learned last semester. And then how do we make this bromide? It's a little tricky. There's lots of different ways you could do it. Personally, what I would do. So let's see here. One thing you can do is you can just add a Grignard reagent to CH2Br2 and then do SN2 to make that. That's probably one of the better ways to do that. You could also take an alkene and then do HBr, H2O2. How do you make this? You can take a carbonyl and then do a Wittig reaction to make that. So either of these ways would work to make that. Either is fine. Once again, there are just so many ways to make these products at this point. We have like 50 reactions. So as long as yours is going to work, you can send me a picture and I can just quickly verify yours would work. If not, this was personally what I would do. I would definitely recommend thionyl chloride for that last step. That's pretty much the only way we know how to do that. But there's lots of different ways we can make carboxylic acids. We can do oxidation, things like that. But there are multiple different ways to do that. This is just how I would do it personally. All right, draw a mechanism for the following hemiacetal formation. So this is an interesting problem because it's intramolecular, which is a little bit hard for students to grasp sometimes. We have our usual step in every acetal and hemiacetal formation. We can have a carbonyl getting protonated and then an OH attacking. We can go ahead and sneak peek at our product to see that it's going to make a 5-membered ring, like that. And then to restore our catalyst, we can use like something like water or sulfuric acid to take that away. And then that will get us here. Hemiacetal formation is not generally favorable, we've learned. So why is the one that is above, though, is favorable, so in the forward direction? How might this be possible? Here we have how many molecules? We have 1, 2. So we have 2 molecules going to 1 molecule. This is the typical hemiacetal formation. Delta S is less than 0, which is bad. In the above example, we have 1 molecule going to 1 molecule. So delta S equals 0, this is more favored. So that's actually better to do intramolecular because delta S is equal to 0. So still, like this late in the game, right? This is a chapter 5 type question. But we still do need to understand thermodynamics to really reason through these hard problems. Predict the product of the following series of transformations, right? So this is a typical kind of protecting group question that we use on this exam where you do some sort of protection. Here we have 2 aldehydes. They're actually identical. In the molecule, this is a symmetrical molecule, so you can add it to either. I'm going to add it to the left. Why did we even add a protecting group? Probably because we only want the Grignard to add at one place. And then we have an acid quench, so we can go ahead and make OH with a Grignard reagent. Like that. H2CrO4, that can oxidize an alcohol into a carbonyl in this case, actually. So it can make carboxylic acids. This one's a secondary alcohol, so we don't have enough room, actually, to make another bond. So we'll go ahead and make a carbonyl. This organolithium can then attack the carbonyl in almost the exact same mechanism as the Grignard. In fact, it is the same mechanism to make this product. Then we deprotect it. So I'm removing the protecting group at this point. However, is this my final product? A lot of you will probably say that it is. However, let's consider the problem we literally just did above. If we have an alcohol, we can't control exactly the amount of acid that we're using. If we have an alcohol and a carbonyl in the same molecule, it will form a hemiacetal intramolecularly. So essentially, right, it's unfortunate that we do have to account for intramolecular steps. But this will go ahead and get protonated, and actually it will form a intramolecular ring. So if the problem above didn't remind you that this actually happens, so how many molecules or atoms are going to be in here? It's going to be a 5-membered ring. So 1, 2, 3, 4. So we will end up forming this. I skipped a deprotonation, but I hope you get what I mean. We will actually form a intramolecular hemiacetal here. So that is tricky because you probably saw this, and I totally would have gotten this wrong on an exam, unless I was designing the question. H2SO4, H2O, that will form a intramolecular hemiacetal. So you need to look for intramolecular reactions is what this question is teaching you. Tricky but important to know. You should be looking for intramolecular ways that things can react with each other. It is important to note. If you didn't get that, you're getting, so say this wasn't like an 8-point question. If there's not a ring in the final product, you're getting 7 points out of 8. So that's not really something to stress about, but just know if you're a perfectionist, it forms an intermolecular ring. All right, here's a reaction that we learned in chapter 19. Show a mechanism of the correct product. So this is kind of like me simulating something that is one of those WTF questions on an exam where you haven't seen it before, but yet it is still possible to be asked about. So, right, we haven't seen this before. We have seen this before, though, and this. We've seen H3O+, we've seen lithium aluminum. So let's see what happens, right? If this was for the sake of remembering, if this was a carboxylic acid, do we remember how this reacted? Our aluminum went ahead and had a hydride come off of it and basically do a nucleophilic or basic attack. Meaning AlAH4 is actually a nucleophile, and then this is an electrophile. So can we rationalize the formation of this product? We actually can. So here, this is the reaction we learned in class. AlAH4, the H can act as a nucleophile and attack. Can it do the same thing here? Yes, it can, except do we have an H in the product? I'm sorry, in the reactant, do we have an H? No, we do not. The question we can ask ourselves, is anything here going to be an electrophile? In the question, the answer to that question is yes, there is going to be an electrophile, and it's the carbonyl. We've seen carbonyls be electrophiles before. Why couldn't we have a hydride go ahead and attack that to form a tetrahedral intermediate, which we have seen before? And then what if that collapsed down and kicked out a leaving group, which we've also seen before in a similar manner, right? We've seen that tetrahedral intermediate kick out leaving groups like that before. Now we have an aldehyde. That's pretty darn close to an alcohol. Except, right, now we have more ALH4. We can probably take a hydride again and add it to the carbonyl. So that's going to give us, right, the product had 2 hydrogens. This had 0 hydrogens over here. This has 2 hydrogens on the product. So we've actually added both of the hydrogens already, and then we can do H3O plus reacting with the base to take that away. That will form the product. So this is tricky because we haven't really seen this reaction before. It's one we learn that next chapter. But it is good to simulate those kind of test questions where you're asked to give a mechanism that is tangentially related to what we've gone over, and you have to be able to predict it based on previous reactivity. All right, now it's on to the textbook problem. So starting with these as the only source of carbon, provide a synthesis for the following alcohol. So one thing we might notice is that carbonyls, right, we have this formaldehyde. We can probably take one of our bromine-containing molecules and form a Grignard reagent with it. That will go ahead and form 1, 2, 3. So we have carbon A from the formaldehyde. And then we have 1, 2, 3. One thing we can do now, so to synthesize, we can either get this back to the aldehyde state, which there really isn't like a super efficient way to do, or we can just straight up transform it into a carboxylic acid, which we have seen before. So I'm going to go ahead and do that, the carboxylic acid step. We can turn this into a acid chloride, or we can go ahead and react it directly, which we've seen before, with a Grignard reagent. That will go ahead and form a ketone. Like that. And then we can go ahead and react it with our last That's very bad drawing. We can go ahead and react it with our last one to go ahead and get that. I hope that made sense. This middle step, right, that's just a predicted product that we did above. So you can react 2 Grignard reagents of the same type to form a ketone containing that carbon group, like that. That's one way you could do it. You could also make an acid chloride. That's a next chapter reaction, so I won't be covering that on this. I won't cover it on this practice exam. We're using 18O labeled ethanol in a Fischer esterification. Which oxygen, A or B, ends up with the label? Did we consider the fact that it could be both? So, I mean, it could be both, right? So we can go ahead and draw the mechanism, even if it seems obvious which one it's going to end up being. It might not be to some people. So we have a electrophile. We add our ethanol. That gives us this diol, or the hydrate, where we have 2 OHs on the same carbon. We can deprotonate that to integrate it into the molecule. At this point, one of these, so you may just be able to recognize here, we're not integrating any more of this. We're not integrating any more of this into the molecule. So what we're going to end up doing is we're just going to end up kicking one of these out as a leaving group, while this other one just gets deprotonated to lose its H. So really, this is going to be B. So 18O, that's a radiolabeled oxygen that's unique, ends up in the C to O bond of the ester. Like that. So it's going to be B. You may realize that because we don't really want to break carbon bonds, and we have both of our carbons from the ethanol here. All right, this graduate student's trying to attempt the reaction, but it doesn't work. Explain why we can't esterify. So, right, we have this carboxylic acid. We have this. Now, the question is, what does this look like? It looks like a nucleophile, but it's also a base. So we're probably going to have to first deprotonate that. Is this a good electrophile? It really is not. It's a poor electrophile. Imagine, though, if we did attack with ethoxide, honestly, this reaction wouldn't be favorable in the first place, but we can try. So, like, this reaction is going mostly in the reverse direction. This is not very favorable. We're going from a carboxylic acid, a carboxylate, which is pretty stable due to resonance, due to something like this, which is really bad. That's not favorable to begin with. If we want to take a look, though, right, to get from here to here, something needs to leave. And the question is anything going to be able to leave unless we have acid present? That actually cannot happen. So, can't happen. Without acid, no good leaving groups form. So we end up being stuck here. It's fine to have one or two unfavorable steps in a whole mechanism as long as you can make the overall thing favorable. But without acid, there's just simply no way to go here. So you actually cannot form that product using base. All right, last problem. In the practice exam, we have a Grignard reagent, which can go ahead and react with that aldehyde. We've seen that several times before. Adding 4 carbons, so 1, 2, 3, 4. And then this problem notes, right, if we don't have an acid quench, so in lieu of quenching the product, so that's telling me that we're not gonna protonate this alcohol, but we're actually gonna use it to attack in kind of an SN2 mechanism to form this product right here. This is actually a Williamson ether synthesis. We just didn't realize it. So Williamson ether synthesis, we learned that in chapter 13. So we form an O that can attack Cl to make it leave. That's a SN2 reaction. So that's the correct product, and we did show the mechanism through that. All right, so that was the practice exam. A little tough, a little tricky examples, but that's kind of what the test is going to be like, so I hope it replicates it well. Advice, right? Predict the products. You know 50 points of predict the products is coming. Prepare for that. Do the end of the book problems. Know your nomenclature. Know your mechanisms. If you're stuck on a problem like this where you're like, what? I haven't seen this before. Try to draw whatever mechanism looks the most similar to the reagent. So just by doing that, you're probably going to get most of the credit for that question based on partial credit because you're recalling something you actually learned. But also, you're more likely to get the question right because you're able to recall essentially how things react, and you're able to predict and go with your intuition on a new situation like this. So here, drawing that carboxylic acid with this previous reactivity of that reagent, that really helped me out. And it would probably help you out in a similar way using pattern recognition to get these right. Got it. So tough exam. So study hard. You guys have 2 days. Thanks for watching.